The learning objective of this chapter is to understand the basic definitions used and the fundamental theory associated with the stability of ships. To understand the terms and theory of heel and list, mass and weight, displacement and dead weight, block and water plane coefficients, Archimedes principle, TPC and moments of mass. It is important to appreciate the difference between the terms list and heel when referenced to a freely floating ship. A ship is lying at an angle of list when the weights on board are unevenly distributed and the static condition of the vessel is at an angle of inclination away from the vertical. A ship is lying at an angle of heel when external forces, such as waves or wind, shift the vessel over to an angle of inclination away from the static condition, perhaps only for a short time. The mass of an object is the quantity of material in that object measured in the units kilogram or ton. The weight of an object is really the gravitational force acting on it, and is dependent on the mass of the object and the acceleration of gravity. Weight is measured in the units Newton, N, or kilonewton, Kn. Therefore, the weight and mass are connected by the formula. Weight equals the mass times the Earth's gravitational acceleration, g. Thus, for a mass of 1 kilo, the weight is 9.8 newtons at most places on the Earth's surface. But for the same mass of 1 kilo, the weight is 1.6 newtons on the Moon. If the acceleration due to gravity is considered constant, then weight is proportional to mass, and in the context of ship stability, we can accept that weight, displacement, is measured in tons. Displacement is defined as the mass of a ship floating in water. This mass is measured in tons, and is normally represented by the symbol delta. The weight of displacement equals the volume of displacement of a ship multiplied by the density of the water in which the ship floats. Dead weight is defined as a measurement of the ship's total carrying capacity. This includes the total weight of cargo, fuel, fresh water, stores, provisions, crew, and items excluding the actual weight of the hull and fixed machinery. The block coefficient, Cb, is a comparison of the ship's actual underwater shape at a given waterline to that of a rectangular box of the same extreme dimensions. The box's height equals the ship's draft, normally summer draft, and the box's length and breadth equals the hull's overall length and breadth. The block coefficient is a measurement that can be used to determine the volume of displacement of a vessel using the formula ship's volume equals ship's length times breadth times draft times block coefficient. Similarly, the water plane coefficient, Cw, is the ratio of the water plane area and the area of a rectangle that has the same extreme dimensions. In order to understand the principles of stability, a fundamental understanding of Archimedes' principle and how it is applied to a floating body is required. The volume of water displaced by a ship can be calculated by determining the underwater volume of the ship, knowing its draft and underwater shape, and then converting this volume into weight of water displaced by multiplying by the density of the water. Alternatively, the weight of the ship can be calculated knowing the weight of the ship's structure, cargo, bunkers, stores, and anything else on board. These two quantities should be the same and are known as the ship's displacement. Tons per centimetre immersion, TPC, is a measurement of how many tons are required to change the ship's overall draft by 1 centimetre. The value of the TPC normally varies with different drafts and possibly different trim and list conditions. If you consider the fundamental theory of Archimedes' principle, TPC will be dependent on the waterplane area and the density of the water, since the additional weight loaded must equate to the additional weight of water displaced, volume times density. The formula to calculate TPC is equal to the waterplane area times the relative density of the water, all divided by 100. This can then be used to calculate the sinkage or rise when the ship loads or discharges a weight by dividing the weight loaded or discharged by the TPC. To measure the weight of a ship, the density of the water in which it is floating is required. This can be found by the use of a hydrometer. Similarly, to measure the weight of a liquid cargo, the density of the liquid is required. There are two main types of density used in stability calculations. Density, which is defined as the mass per unit volume of a substance. The units for density are normally tons per cubic metre. Relative density, which is the ratio of the weight of a substance and the weight of an equal volume of fresh water. It has no units. The moment of a force or mass is the measure of the turning effect of this force about a specific point and will be dependent on the size of the force and the length of the lever from that point. The moment equals the weight times the distance from a specific point. In stability problems, this would normally be expressed in tons meters. This chapter introduces the importance of determining the centres of buoyancy, weight and waterplane areas, and to understand how these centroids or centres can be shifted. The centre of area of a plane surface is the geometric centre of that area. A ship is in equilibrium when the weight forces acting downwards through the centre of gravity G and the buoyancy force acting upwards through the centre of buoyancy B are in the same vertical line and are of the same magnitude. The perpendicular distance between the ship's centre of gravity G and the vertical upthrust through the ship's centre of buoyancy B is known as the righting lever, and given the value Gz. This is the lever that is created when B and G are not in the same vertical line, and provides the couple to return the vessel upright after being inclined over by an external force, such as a wave. The value of this lever is plotted as the y-axis in a graph known as the curve of statical stability. This will be discussed later in the course. As described previously, the moment of a force is a measure of the turning effect, and when considering the righting lever Gz and the force of the displacement, this righting moment is known as the moment of statical stability. Units ton-metre. When a weight is shifted on board, loaded onto or discharged from a ship, the original centre of gravity of the ship will move parallel to a shifted weight, directly towards the loaded weight, directly away from the discharged weight. On a ship working cargo, this will normally result in the centre of gravity G moving at an angle from the centre line. To make this easier to calculate, the movement is normally broken down into two parts, the horizontal movement and the vertical movement. A weight already on board is lifted from the deck using the ship's derrick, which is plumbed directly over the weight. As the weight is lifted off the deck, the centre of gravity of the weight will instantly move vertically upwards to act at the point of suspension, the derrick head, and the centre of gravity of the ship, G, will move accordingly. The vertical distance, D, moved by the centre of gravity, G, of the lifted weight, will obviously be large, deck to derrick head, and the vertical shift of the ship's centre of gravity, G, will move a large distance accordingly. This can be calculated by the following formula. GG1 is equal to W multiplied by D divided by displacement. A ship is loading a weight from the quay using its own crane or derrick. The ship's centre of gravity will follow the movements of this loaded weight during the various stages of loading. It will move upwards and outwards towards the derrick head during the initial lifting off the quay, back parallel to the swinging derrick head, and finally upwards and outwards from its original position towards where the weight is eventually placed on the deck. The final position of G would obviously be different to its original position before loading, and the overall displacement would have increased by this added weight. The above formula should be repeated 4 times to determine the various positions of G during the loading process. Vertical movement of G when the weight is suspended by the derrick over the quay, where D is the vertical distance from G to the derrick head. Horizontal movement of G where d is the horizontal distance from G to the derrick head over the quay. Horizontal movement of G when the derrick swings the weight from quayside over to the final position of the weight on the deck, and d is the distance moved by the derrick head. Vertical movement of G when landed on the deck, where d is the vertical distance from G to the G of the weight on the deck. When a single weight is loaded, discharged or shifted, the new G can normally be obtained in a single calculation by taking moments about the original centre of gravity, G, as shown previously. However, when a series of weights are loaded at different positions on the vessel, the most effective method of calculating the new centre of gravity is to use a table of moments. When the transverse centre of gravity is required, it would normally be calculated by taking moments of all the weights about the keel. If it is the longitudinal centre of gravity that is required, it would be calculated by taking longitudinal moments about a point such as the after perpendicular. The total vertical moments would be the sum of each weight multiplied by its distance from the keel, and the result would provide the position of the ship's centre of gravity from the same reference, the keel. The final kg of the vessel is calculated by a table of moments as shown, where the final kg is determined as 4.41 meters.